In this video, we're going to talk about section 3.3, which is called uninhibited and limited growth. And to do this, we're going to introduce the idea of something that's called a differential equation. So a differential equation is a special kind of equation. And basically what it does is it relates the derivatives of a function to the actual function itself or other values that are constants and different expressions of the function itself. So, for example, the differential equation that we're going to most look at is dy dx is equal to k times y. And so dy dx is equal to k times y. It says a derivative of y with respect to x is equal to some function, some value k, which is a constant, times a function y itself. Okay? So unlike a regular equation, which would be something like x squared is equal to 4, where we could say x is equal to plus or minus 2, in the case of a differential equation, our equation is going to be a function instead of an actual number. So if we were to look at this, this is what's called the growth equation if k is positive. What we're going to see is that the solution to this equation is a function. So when we have dy dx is equal to k times y, the solution is going to be y is equal to c times e to the kx. So what this is saying is that if the derivative of a function y with respect to x is equal to some constant k times a function itself, then the equation or the function that satisfies that is y is equal to c times e to the kx. And so we're not going to talk about why this is a proof of the equation, but what we can do is we can prove or show that this is indeed a solution to this equation. So let's say that this is our function y is equal to c times e to the kx. Then what we can say is that dy dx is equal to d dx of c times e to the kx, which we can pull the c out in front and say this is c times d dx e to the kx. And then we know from what we've been doing with the derivatives of exponential functions that this derivative right here is going to be k times e to the kx. And so what I can do is rewrite this as k times c e to the kx. But if y is equal to c times e to the kx, then this here is equal to y. So this is k times y. So this tells us that if y is equal to c times e to the kx, then dy dx is equal to k times x. So this doesn't tell us this is the only solution, but for our purposes, this is the only solution. This is a way that will show that this is the only solution. So we can see this in a number of different ways. Let's look at some examples. Let's say that, for example, we have something like this. We have dA dt is equal to 7 times a. So from our previous slide, we saw that dy dx, if dy dx is equal to k times y, then y is equal to c times e to the kx. So in this case, I have this here as my dy dx. So y is like a, and t is like x. So my solution in this case is that a is equal to c times e to the 7t. Okay, so looks like there's a negative there. Get rid of that. So this here would be the solution to my equation, because if I took the derivative of this right here, then what this would tell me is, if I took the derivative of this right here, I would end up getting 7 times this function c e to the 7t, which is 7 times a. All right? So one of the solutions or one of the applications we're going to look at most is we're going to look at population growth. And here in population growth, our y is going to be called p, and the x variable is going to be time. So we're going to have something like dp dt is equal to k times p. That looks like our original expression, dy dx is equal to k times y. And so here we can say that the solution is p is equal to p naught e to the kt. So let's say that in this case our p represents some population of some country or some state or something like this, and t is given in time. Then if the rate of change of the population with respect to time is equal to some constant times the population, then we can say that the population's behavior is going to be exponential growth. So this here is an exponential growth if k is greater than 0. Okay, and in this case, our graph of this would look something, if t is greater than 0, something like this. Okay, so right here, if we have this is t and this is our population, then here when t is equal to 0, we have some value that is going to be p0, because at t is equal to 0, I can say that p is equal to p naught e to the k times 0, which is p naught times 1, which is p naught. So at t is equal to 0, p is equal to p naught. So this p with a little 0 as a subscript, we pronounce as p naught. And p naught, we can say, since it's a population at t is equal to 0, is our initial population. Okay, so let's say that we have an example of this, and sometimes we're going to use this for population growth, and another example we're going to use this for is what's called compound interest. So let's say that we have, okay, so one example that we'll use for business and economics to apply this idea of uninhibited growth or exponential growth is what's called continuously compounded interest. So compounded interest means that periodically you receive interest on an investment, and then once you receive interest on the investment, then you'll also receive interest on that interest. So the idea of continuously compounded interest is that you get your interest compounded continuously. So you receive interest immediately at a certain rate, and then that interest gets interest. So it's almost like you're receiving interest at every instant of time. So let's say, for example, we have an investment of $100 is continuously compounded at a rate of 7% per year. All right, how much is in the account after 3 years? Okay, so what we're going to do is we're going to start by writing our growth equation. So it turns out that if we have continuously compounded interest, then we can also use the equation we looked at for population growth, which is dp dt is equal to k times p, where k is our annual interest rate, and p0 we're going to say is our initial investment, and p is the amount in the account. Okay, so if we have an equation, differential equation of the form dp dt is equal to k times p, then what we've seen is that the solution looks like this. All right, so this here is going to be our general solution. And then in the particular case we have a 7% interest rate, which we're going to put into decimal form. So this annual interest rate we'll write as a decimal. And P naught, which is our initial investment, is $100. So what I can do is say that P is equal to P naught, which is $100, times e to the 0.07t. Okay, I could have written my original equation as dp dt equals 0.07. Is that this here is equal to $123.37. All right, so again, you'll see some of these problems on your quiz and on your practice test, that this here will be our differential equation for describing compound interest, which is compounded continuously, and the P is going to be the amount of the investment, K is going to be the interest rate that's given in decimal, so in this case, this here is going to be our equation. And then once we get to the general solution, P naught is going to be our initial investment, which in this case is $100, and T is going to be the number of years, which in this particular problem is 3. And if we plug all that in, what we end up getting is that the amount in the account using the calculator is $123.37.